Of course, one of the defining things about carboxylic acids is that they're acids. Imagine a general acid here. Here comes a water molecule. Now, we can think of this in two ways. We can start off by thinking it as a Lewis acid-base reaction. Here we have the oxygen, which has electrons to spare. It can donate those electrons. It can be a Lewis base. And it donates them to that hydrogen, which accepts them. Thus, this becomes the Lewis acid. And of course, once the hydrogen accepts the electrons from this oxygen, it tells this oxygen to get lost. And so we have a Lewis acid-base reaction, giving us this. Okay. Now, the other way to think of it is, of course, as a Bronsted-Lowry reaction. Here's the acid. It donates a proton to the H2O, making H3O+, leaving behind its conjugate base. Now, let's focus on this conjugate base for a while, okay? Because you've got pi electrons here, and you have electrons here in lone pairs on p orbitals that can serve to act as pi electrons as needed. And so you get stabilization by resonance. So you've seen this several times before. The electrons from this oxygen can pop on into that double bond. Okay, just make a double bond there, at which point the carbon says, well, I don't want these pi electrons anymore. So those just do the opposite and become a lone pair on the oxygen. And so you have this resonance structure. So you've got special stabilization by this resonance because of the movement of pi electrons. Essentially, this oxygen can be negative, or the double bond. This oxygen can be double bond, or it can be negative. Now, of course, reality is the average of those things put together. So here you've got the R carbon, oxygen. I've spread out the electrons. We've delocalized those electrons and just said it's a general negative sign. Now, the importance of this can be seen by matching bond lengths. When you take a carboxylic acid, in which, of course, one of the oxygens is a double bond, the other oxygen is a single bond, because that's the oxygen that's bonded to the hydrogen, you see distinct different bond lengths. Carbon-oxygen double bond, 121 picometers. Carbon-oxygen single bond, 136 picometers. When we look at this resonance average over here, both of those bond lengths, the carbon-oxygen bond lengths, are equal at 125 picometers. What that's telling us, in the same way that the equal carbon-carbon bond lengths in benzene told us this, is that this electron that's left behind when the hydrogen goes is stabilized over all of this whole system. It's extra stabilized by resonance. That means that carboxylic acids are good acids because when they lose that proton, the conjugate base is a nice, happy, stable species. Now we can compare that to phenol, in which, of course, the conjugate base, the phenolate anion, was also stabilized by resonance. But that resonance in phenol is not as good as the resonance in carboxylic acids. Carboxylic acids are better acids than phenols are. Now, of course, poor old alcohols, which is another one to compare, are absolutely duff acids. And the reason for that is that if they do their little acidic bit, so you make the conjugate base right here, there's absolutely nothing to stabilize this electron. This electron's stuck on the oxygen. Oxygen isn't that keen to have that extra electron. It would rather have a hydrogen to bully. And so alcohols, terribly weak acids, so weak they're hardly weak at all. They're hardly acidic at all because they have no way to stabilize the conjugate base. Very, very important that you appreciate that carboxylic acids are good acids because they have a nice, stable conjugate base. If we compare K values, just to really emphasize this, just take the second simplest acids and alcohols, so ethanoic acid and ethanol. Right, the Ka value is ethanoic acid, 1.8 times 10 to the minus 5. It's a weak acid, but it's very distinctly acidic. Ethanol, 1.3 times 10 to the minus 16. It's not an acid at all. Or if it is one, it's weaker than water. Water, of course, being 1 times 10 to the minus 14. Let's stay on acidity and look at the different acid strengths of different carboxylic acids. First, let's consider just the alkyl carboxylic acids. Start with methanoic acid, in which we just got an H, Ka 1.8 times 10 to the minus 4. Replace that H with CH3 to give us acetic acid, 1.8 times 10 to the minus 5. We get significantly weaker by a factor of 10. Add in a little bit more of the alkyl and we get a little bit weaker, 1.4 times 10 to the minus 5, smaller, 1.8 times 10 to the minus 5. Throw in a couple more alkyl groups there, 1.4 times 10 to the minus 5, but then put in 3 alkyl groups on that carbon, we go down to 9.3 times 10 to the minus 6. So the more alkylness we have stuck on there, the weaker the acid gets. And that's because alkyl groups, if you remember, are inductively positive. They have a positive induction effect. They push electrons towards the carbon here. Okay, now remember what this carbon's got to do if it's going to be an acid. It's got to lose a hydrogen, so it has to accommodate some extra negative charge. Well, if you've got something here pushing even more negative charge onto that carbon, the carbon's not going to be as happy to let the H go. The more electrons pushed towards the carbon, the weaker the acid is going to be, because the more electrons that are pushed towards the carbon, the less it's going to want to have another electron in there because of the hydrogen that goes away. So alkyl groups added on make the acid weaker than formic acid. Now, can you think about the flip of that? What if we think about having some halogens there? Okay, because of course halogens suck electron density away. They have a negative inductive effect. So let's just take, instead of acetic acid or ethanoic acid, let's replace one of the hydrogens by a fluorine. So that fluorine's sucking electron density away. Even though it's quite a way away from the carbon, look at the effect it has on Ka. It goes from 1.8 times 10 to the minus 5 to 2.5 times 10 to the minus 3. That fluorine sucking electrons away from that carbon means this carbon is happier to lose that H+, happier to get the extra electron density because it's got something to help relieve it. Instead of fluorine, put a chlorine there, and of course the acid becomes weaker. It's still 10 times stronger than acetic acid, but because fluorine much more electronegative than chlorine, chlorine can suck those electrons away. Place the chlorine by bromine. Well, chlorine and bromine, there's not a huge difference in electronegativity, so you don't see a huge difference in the acid strength. Now, going on and replacing, instead of one hydrogen by chlorine, let's replace 2 hydrogens by chlorine. So now we've got 2 atoms sucking electron density away from that carbon, makes it an even stronger acid. We go from 1.3 times 10 to the minus 3 to 5.1 times 10 to the minus 2. And put in a third chlorine and you get up to 1.3 times 10 to the minus 1. You're pushing, getting to where some silly people would argue this is almost a strong acid. Look at the size of that Ka. So the halogens that you put in, they have a negative inductive effect. They suck electrons towards them. Sucking electrons towards them in this case makes it easier for the carbon to lose the H+ there, because you got some help taking care of the extra electron density. Now it's interesting to just see how distance affects this. So a little series here where I'm taking some butanoic acids and first of all putting a chlorine on the second carbon, right? So it's carbon right adjacent to the acid, 1.6 times 10 to the minus 3. Okay, and now let's move it along one carbon, 7.9 times 10 to the minus 5. Move it along one more carbon, 3.2 times 10 to the minus 5. Well, that's pretty close to the actual acidic value of where you have no chlorines in there. So putting in halogens makes the acid stronger. The more of them there are, the better, and the closer they are to the acid group, the better. Some very important typical electronic trends to think about there: the positive and negative inductive effects, and then the way in which those negative inductive effects in particular are affected by, first of all, what atom is doing the negative inductive effect, how many of them there are, and how close they are to where it's counting. I do want to spend a slide on conjugate base anions because, of course, when our conjugate acid loses a proton, it makes its conjugate base, which I'll draw here in the 1 resonance form. Remember, of course, this negative charge is spread out over both of these oxygens. But anyway, these conjugate base anions are very, very important. You've seen them so many times, you've heard about them so many times, and you should always be aware from where they come. The name of these is we take the anoic acid and we turn it to anoate. So thus, methanoic acid loses a proton, it makes methanoate, otherwise known as formate, which I'm sure you've heard of. Ethanoic acid makes ethanoate, otherwise known as acetate, which I know you've heard of. Propanoic acid loses the H+ to make propanoate or propionate. Continuing on, just removing protons from all of my sample acids. So butanoate, pentanoate, propandioate, which is much better known as malonate. That is the dianion that comes from both of the acid groups of malonic acid losing their protons. Benzoate that you see a ton of, acrylate, which is very important in polymers, you must have heard it with that, and then of course lactate is the anion that comes from lactic acid that other people would call 2-hydroxypropanoate. So do be aware that when you see a organic-y type prefix followed by anoate, it means it's the conjugate base anion from a carboxylic acid. Now, of course, acids react with water to make H3O+ and the conjugate base. They also react with bases, and so you have the very GCSE acid-base neutralization reaction. Acid plus base goes to salt plus water. And it's important to note that carboxylic acids do all of the reactions that you would expect from acids. They'll react with hydroxides quite happily. So acetic acid plus sodium hydroxide makes sodium acetate or sodium ethanoate plus water. We talk about the reaction of weak acids with strong bases extensively in the acid-base module, and we do calculations on it in the acid-base module extension material, so you've seen that before. They'll also react with oxides. Now remember, all oxides are their hydroxides that have lost some water. So if we took 2 acetic acids to react it up with copper oxide, this is a reaction that you'll have seen in the A levels. Well, again, you're going to get a neutralization. There's the H, there's the start of the base, the oxide there. So you'll make some H2O. And of course, you also make the copper acetate, that's the salt. This is a nice little test that you can do in some places. You start off with the black solid of the insoluble copper oxide, and then that reacts and dissolves in the acid to give you the nice blue solution of copper 2 acetate. Another test that we can use is to react up the acid with carbonates or hydrogen carbonates. You have to be a fairly decent acid to react with carbonates. So phenols don't, but carboxylic acids do. And when they react, they ultimately make the salt again, sodium acetate, you make water, and you make carbon dioxide, and we can draw the same reaction using sodium hydrogen carbonate. Again, the sodium's going to be there to grab on to the conjugate base. You make water and carbon dioxide. Nice tests for acids in general. Like I say, they have to be strong enough. So this gives you carbon dioxide when you do it with a carboxylic acid. When you do it with phenol, it doesn't react. Phenol, while acidic, is not a strong enough acid.